Okay, guys, we'll be starting now. Okay, so yo guys, I'm Karen, and today I'll be talking about a map in the night sky. Can y'all hear me? Okay, nice. So, have you ever looked up in the night sky and wondered why do some stars seem to move more than others, or why they even move at all? Or looked at images of the Orion constellation taken in Australia and wonder why is it upside down? Or wonder why you never seem to see Polaris, the North Star in Singapore, even though it's actually quite bright? Well, if you didn't, then come down when we have physical stargazing sessions and we'll give you things to wonder about. So when we stargaze, we should by right see a sky full of stars. And that's what people in ancient times saw too. They came up with constellations both as a way of remembering the patterns of stars, as well as to give meaning to the celestial powers that they believe the stars hold. But the depiction of constellations is actually not very spatially accurate. For example, the constellation I have here on the left, which is Cassiopeia, meaning the queen, looks like a W. We might think, oh, okay, if we see this in the sky, this star is closer to this star compared to this other star. But in actuality, the stars are actually very far apart. These two stars are actually very far apart. These two stars are actually very far apart over here compared to these two. So what we see as constellations in the night sky is actually a 2D depiction of where the stars actually are in 3D. But for observation purposes, that doesn't really matter. We're not really trying to reach the star. we're just trying to observe it. Hence, we have a nice 2D spherical projection of all the stars and celestial objects we can see, known as the celestial sphere. So this celestial sphere of stars around the Earth, as you can see in the image, is similar to the Earth actually, where the north is projected from the Earth's north. So the north celestial pole in the celestial sphere is projected from the Earth's north pole, directly upwards. Whereas the south pole, the south celestial pole over here, is also directly projected from the south pole. And the celestial equator is also a direct projection of the Earth's equator. So while it might seem that the celestial sphere seems very close to the Earth, the stars are actually really, really far away. So what it actually looks like is a bit more of, for example, this tiny red circle is the Earth, and the celestial sphere is very huge. Like this is not even to scale, okay? My circle is a bit not very circular. But so that's how you can imagine how if we are just a person standing on the Earth, we can actually see the half hemisphere of the celestial sphere, minus all the trees and buildings. So now that we have this nice celestial sphere, it actually makes our map a lot simpler. We only need 2 coordinates for each object. So of course, we don't have to define how far away it is from the Earth. So the less ancient people, more recent people, started using right ascension and declination. So at first you might think, okay, these words sound very complicated. What do they mean? But it actually kind of makes sense after we see what they mean. So on the celestial sphere, the declination is similar to latitude. So you can remember it by thinking decline means to go down. So the declination is along the lines of up and down. So from the celestial equator, if you go up, it's positive declination from 0 to 90. Whereas if you go down, it's negative declination from 0 to minus 90. Meanwhile, right ascension is similar to longitude. On the Earth, we take longitude with reference to this place called Greenwich in England, which is taken to be 0. For the celestial sphere, we do have something similar where we take the first point of Aries, which is the Aries constellation, as 0, and then move 24 hours then increase to 24 hours as we move eastwards. Hence, ascending as we go right, aka right ascension. So nice. Now we have a map to tell us where is the stuff we see in the sky. But now you might be wondering, wait, how can this map work? Don't the stars move? So does the map move as well? Well, actually, yes and no. So the stars don't actually really move, or at least, So the stars don't actually really move, or at least like not significant to us stargazers in our lifetime, but the Earth moves, or more specifically rotates. So that's why the star appears to move relative to us. So if we are on the Earth and the Earth rotates, then the stars will now seem to move along the lines of right ascension. So like a few seconds for that to sink in. So now this will all make sense if we were on a spaceship looking at the Earth from afar. But how does this map actually look like if we were on the Earth? So actually that depends on where you are on the Earth. So if we are in Singapore, we are actually somewhere near the equator. So the declination lines, we call that declination means to move downwards. So we have one line at the celestial equator over here, one line slightly towards the south celestial pole, and one line slightly towards the north celestial pole. Then the declination lines will look something like this to us at the equator. And so, okay, if you can see my hands. So if we're at the equator, right, and we look at the sky and we like fast forward or something, how it will look like to us, the sky will appear to turn this way, if like this is the ground. So the sky will appear to move like this, not back and forth, but one like that then the stars will appear to move from east to west. So, but if we were somewhere near the north, over here, if you were somewhere at the north, then the celestial sphere will appear tilted. So now instead of like this, it's now like this. So it will appear to move like this, where like the middle of my palm over here would be your north celestial pole. And in the south, it's tilted the other way. So it will spin like this. And you might think, okay, wait, this is very confusing. How does this link to the earlier diagram of the celestial sphere we saw earlier? So if we, okay, let me try to draw this. If this was our Earth, and this was the nice big celestial sphere we saw earlier, then let's say that this is the equator, because remember that the Earth's the celestial equator is a projection of the Earth's equator, so it'll all be in one line. So if we are on the equator, okay, then after that you have all your declination lines, something like this, right? And then you have your north celestial pole over here and your south celestial pole. So if we are on the equator, that means we're standing somewhere here and we're looking upwards. So this is our ground. Then it will make sense, right? So this is our ground, and then it looks something like this. So the stars will appear to rotate, move from east to west with the north celestial pole here and the south celestial pole here and all the line and all the stars above us. Whereas if you were somewhere in the north, let's say, okay, let me erase this ground. Let's say instead of being at the equator, you're somewhere at the north over here. So your ground is like this. So if your ground is like this, and I extend your ground a bit more, then now when you look at the sky, you actually see the north celestial pole here, and all the stars appear to revolve around it. And then in the south, your ground will be here, so it will be the opposite over here. Okay, so hope that was understandable. So this is how it will look like. So if we add the part where the celestial sphere appears to move relative to us, it will look something like this. And actually, this is how people take pictures of star trails, by aiming their cameras at one of the celestial poles covering the movements of the star around the pole. And this also means that, if we understood from the slide earlier, if we tried to take star trails in Singapore, they won't really look like the nice circles we see in pictures. They will actually just look like rainbow arcs. So remember near the start, I said some of y'all might be wondering, why does the Orion constellation appear upside down in Australia? So the Orion constellation, which I sort of drew, which is over here, actually appears somewhere near the celestial equator, which means you can almost definitely see if you're both in the northern hemisphere and the southern hemisphere. In the north, we see Orion something like this. But if we see Orion something like this in the north, and we are somewhere here, and we look up, we see Orion upright. Whereas if we are somewhere in the south, and Orion will appear something like this, and then we would now stand over here, but instead of looking towards the north direction, we will look a bit more towards the south direction. We'll look here, and then we'll see Orion as upside down. So this is why it appears upside down. But then this phenomenon, or having constellations appear upside down in the southern hemisphere, is really only for constellations that appear past the point right above you. So for example, if this is the point right above you, Orion is towards here, so that's why it appears upside down. Whereas if you had a constellation, for example, the Southern Cross, which is like a cross over here, in the north, it will look like a cross over here. In the south, it will still look like a cross over here. So it will still be both upright. So this is all nice and stuff, just that there is a tiny issue. Not everything is fixed on the celestial sphere. Wait, why? So remember earlier I mentioned that the celestial sphere doesn't really change because any movement of the stars is sort of negligible in terms of the scale of space and time. Well, that isn't really the case for our planets and the moon. So the planets actually move a noticeable amount through the sky if you compare between months. Like you see over here, like now Jupiter is somewhere near this Capricorn, near these two stars. And then 1 month ago, it was above the two stars, and 2 months ago, it was like barely even in Capricorn. So in fact, this is where the word planets come from. It actually comes from the Greek word planetos, which means wandering star. And in fact, the position of the moon varies even more between days, where it moves enough between days. So this is at the same time, I'm just moving between the days, right? It moves enough to go 1 round around the celestial sphere in a month. So this sounds quite bad. Does that mean the planets can be anywhere in the night sky and we just have to try to look out for these bright dots? Well, thanks to some physics that happened during the formation of our solar system, the solar system is actually quite neat, where all the planets move along the same plane. This means that if we are on the Earth and we erase the ground, the planets would appear close to a ring on the celestial sphere, this red line that we can see. This ring is known as the ecliptic, which nicely traces out the path of the sun. And nicely as well, the moon actually orbits around the Earth on a plane very close to the ecliptic. Now you might be thinking, ecliptic sounds familiar, sounds like some kind of sweep. Well, actually, it came from the same Latin word as where the word eclipse came from. So now we know to find the planets, we can look along the line of the ecliptic in the sky. And you can technically roughly look along the same line to find the moon somewhere near there as well. But if the moon is up and you have to find the moon, then maybe you should just find another night to stargaze. And okay, so small tangent. The ecliptic on the celestial sphere also happens to nicely trace out a nice ring of constellations known as the zodiac constellations. So remember, the stars are all on the celestial sphere. So imagine that we just take out the ring, take out a ring of the celestial sphere corresponding to where the ecliptic, which is the red line we saw just now, was. So it happens to correspond to the zodiac constellations. So is this a coincidence? Well, it's actually not a coincidence. So how the zodiac constellations came about is back when the Babylonians, about 2000 plus years ago, came up with the zodiac constellations and horoscopes and stuff. They recorded the constellations in which the sun was in over a period of days, which is how the term sun signs came about. This means that if you are an Aquarius, back then the sun was in a constellation Aquarius in January. What this also means is that if you really want to see your own zodiac constellation, you can't actually see it in the night sky on your birthday, else you'll be looking somewhere near the sun, which you shouldn't do. So you have to wait about 6 months or so, and you can see it somewhere in the night sky. Now, going back to the celestial sphere, with all the pros of it, it also comes with some cons. So one of it is what we just mentioned, which is that stuff that move won't have fixed coordinates. So how do we sort of indicate to each other, like indicate where the planets are? And another is that for regular stargazing, you might want to just know where the star is in the night sky without having to do any math. So this is where we have another map. This map is a lot more intuitive. So firstly, on an imaginary sphere, another imaginary sphere, where the top half of the sphere is the hemisphere you can see above ground. So now you are here. And this is just any ground you can be on. It doesn't matter location or timing or anything. So the top half of the sphere is, which is what you can see above ground. So then the point right above you is called the zenith. And the point right below you is called the nadir. And there's a nice line connecting the Earth's north direction, the zenith, and the Earth's south direction, which is called the meridian. So now you kind of know what the term wait for the object to reach the meridian means, if you ever heard about it during stargazing sessions. So a small tangent about why this term is being used. So generally, as we understood from how the stars move, they'll move from the east to the west, passing by the meridian. It is generally better to see an object when it's near the meridian, because the light from the stars go through less atmosphere from above us than from near the horizon. But GG, you're next, so up to you. And then back to how these observer coordinates work. The two coordinates are called altitude and azimuth, or LS for short. Altitude, as the name suggests, is how high the star is. Hence, it starts off from 0 at the horizon, all the way up to 90 at the zenith. Azimuth starts off from 0 degrees at the north and increases towards the east. This is a really easy coordinate system to use, since you can usually just estimate the altitude by looking from the horizon up to the zenith, back to the star to aga-aga, and then use a compass to get the azimuth value. So that means if you and another person are both at the same location, you can technically tell the other person the azimuth value, the LS coordinate of whatever object you're looking at, and he should be also able to roughly estimate where the star is. Okay, so Susan just asked, how do you get the azimuth at the North Pole? So remember I said that LS doesn't depend on what location you're at. It just depends on where the star is relative to you. So that means if let's say I'm assuming, let's say you want to get the azimuth of Polaris, so it will just be directly above you. So it will just be 90 degrees if you're at the North Pole. Okay, if I got that question correct. Okay, so now we'll sort of have a little break on content and have a nice little activity to see how the right ascension and declination lines would look like in the night sky. So here we have supposedly a night sky, and here, over here is where the South Pole is, and then the location that we are at Singapore. So it's somewhere near the equator. So given that this is the South Pole, how would our right ascension and declination lines sort of look like in the night sky? If anyone would like to try. Okay, I will try to give a clue. Let me think. Okay, so this is how we are looking at the sky if you're on Earth, right? So let's say if you were looking back at the celestial sphere diagram, if this was the Earth, and this is the celestial sphere, then we call that this would be your north celestial pole, which is a projection of your North Pole. And this is south, and this is the south celestial pole. And recall that your declination lines would look something like that. And your right ascension lines would be something like that. Okay, it's a bit messy. So now we're at the equator. Equator means our ground is somewhere here, and we're looking up. So how would these lines sort of look like if we were now on the Earth instead? Okay, wait, someone drew something. Wait, let me see. Yeah, so as you go up, your declination will slowly increase. Yeah, because we're at the equator. Okay, or if it's a bit difficult, then I guess is anyone still interested in trying? Okay, if not, then just show how it roughly looks like. Yeah, so this would be how your right ascension and declination lines would sort of look like if you were on the equator, which is at Singapore. And if you look towards the south, so remember that the south projects towards the south celestial pole. So that means the stars will sort of revolve around the celestial poles. So these would be your declination lines all the way until the celestial equator. And this would be your right ascension lines. So, and then we see over here that we see this is in degrees, and then this is in hours. So our right ascension lines are in hours. If we recall, starting from 0 all the way to 24 hours as we move eastwards. and then our declination lines will sort of start off from, and then you notice that over here is this 35, and then this slowly goes to 30, right? So this shows that if we move towards the self-celestial pole, it will be at -90 all the way until 0 at the celestial equator. Okay, so now let's try for altitude and azimuth, which should be slightly easier, and see how it differs from right ascension and declination. Anyone would like to try? Yes, so actually the direction of the lines are correct. Yeah. So the altitude and azimuth lines actually look like this, which is actually why it's, as I mentioned, it's a bit more intuitive, because when looking up at the sky and use the altitude and azimuth coordinate system, right, it feels like your X and Y axis. So it's just up, down, and left, right, which is why it's a lot more intuitive and easier to explain, or easier to explain, like easier to refer to the stars. Yes. So with that, so now we see that like each map has its own purpose, but it's always nice to know like how both of them works, which is why we're covering both today. So now hopefully you can draw your own red cross on the map of the night sky and go treasure hunting. Yep, so that's the end. Okay, so don't worry if you were not able to fully visualize everything right now, because hopefully one day when you're stargazing, it will suddenly make sense, as it did for me. And to avoid going on too many tangents, I left some things hanging. So if you have any questions, just feel free to ask. Okay, because if you don't have any questions, then hope you all remembered some things, because now we have a Kahoot quiz. Okay, can you all see my screen? Yes, so feel free to join our combined top winners at the end of the semester. Will win something. Is anyone else joining? Okay, if anyone is still joining, please sign off in the chat. If not, I'll start in a minute. Okay, I think I will start. Oh wow, okay. Is there any more people joining? Okay, legit no more there. Okay, I think I'll start. Best of luck. Okay, nice, not bad. Most people got it right. So, okay, a bit sad for whoever fell for left ascension. So if you all remember, your right ascension value increases towards the right. Yes. And the zenith and nadir is not a coordinate system because zenith is actually, these two are actually part of your altitude and azimuth coordinate system, where zenith refers to the point right above and nadir the point right below. Yes. Okay, I like how I'm somehow winning even though I'm not playing. Okay, nice. So right, okay, I thought people would fall for this, but apparently not. Okay, so the reason why it's 89 degrees is because Polaris is kind of near the North Star, so you can kind of just assume it to be at your North Celestial Pole. And then if you remember, at the North Celestial Pole, our declination coordinate will slowly increase to positive 90, so it should be somewhere near 90. Yes. Ours is for our right ascension, so it's not the units for declination. Not bad, not bad. Okay, so this was a bit more difficult question because I did mention that like the planets move. So it's like they're not fixed. So they don't have fixed right ascension declination coordinates, but they do have them. Okay, nice. So right, if you remember, the ecliptic is the path, is a ring on the celestial sphere that traces out the path of the sun. So the sun must be there. And then the moon's orbit plane is near the ecliptic also. So the moon can also be there. And then the path that the sun traces, because the solar system is kind of flat. So the orbits all like trace on the same plane. So Mars is also there. But Polaris, the North Star, is nowhere near the ecliptic. So yes. Okay, nice. So if you remember, the difference between the two coordinates was that for stars, which is Orion, because Orion is a constellation made out of stars, the right ascension declination should be roughly the same. Or like, okay, in the span of time, it should sort of be the same, because that allows us to use a coordinate to define the stars regardless of time, location, or place. But the altitude and azimuth will be different because that depends on your location and time. Aha, so this was more of a trick. So, okay, so those who answered yes, I think you all remember what I said earlier with regards to the Southern Cross. So that one, back then it was correct, but then it depends on where you are. Because now your friend is no longer just anywhere in the South Hemisphere. Your friend is at the South Pole. And what is interesting about the South Pole is that the South Celestial Sphere is directly above him, which means that all the stars just look like they are revolving in circles around him. Which means that the Southern Cross, okay, let me see if I can draw this out, maybe it'll be easier. Let's see. So in Singapore, North, South, Celestial Pole, when we look at the Southern Cross, it kind of looks something like that. So let's say like, okay, let me make the bottom a bit longer to show that this is like how it looks like upright. So we see it upright like this. But if your friend is at the South Pole, that means he's looking straight up like this. Everything at the South Pole will appear to be upside down. Because if his brown is now like this, which means he's now like this, looking at the South Pole, then this Southern Cross will now appear to be like this, along with everything else at the South Pole, because now everything, yeah, so your friend at the South Pole just sees there's no south star, because there's nothing exactly right at the South Celestial Pole, but everything will appear to be revolving around the circles like this. Yes. Okay. Let me erase that. Okay, this is interesting. Why is this so divided? So by right, all stars will pass through the meridian because where's my drawing? Okay, wait, where's the pen now? Okay, don't know why the pen suddenly doesn't work. But then we recall that the meridian is the line tracing from the north, as we see on Earth, through the zenith, through the south. So all the stars that we see in the night sky will definitely have to pass through the meridian as they move from east to west. Yes, so as you remember, the celestial sphere is just a projection of all the stars that we see in like infinite, not infinite, but sort of infinite space. So it's not an actual one nice sphere of stars. If not, I think that would be a bit chaotic over there. Okay. Let me see. Interesting. Okay, I'm not sure if those who answered through maybe like misunderstood the view of it, or maybe like maybe it wasn't clear. Okay, so back in the slides when I explained, right, your right ascension, when you look at the celestial sphere, the north celestial pole is at the top, the south celestial pole is at the bottom. So it increases as you move eastwards towards the right. Yeah, which is why right ascension. But yes, so by definition, it increases as you move towards the east. Yes, so it's at the north celestial pole. It's not on the ground. It's not in the sky. And to those who click the North Pole, I'm a bit sad, but yes, so our North Star is at the North Celestial Pole. Okay, so congrats to all for winning. Can the top 5 people just PM Chun Song? Then cause we need to like just PM with your actual name so that we can, unless you don't want to be in the running for a potential prize, then your real name, like which corresponds to your whichever name over here, so that we can collate your score. Yes. Thanks. Hope y'all learned something today and had fun. Okay, now I'll pass the time over to Nick Tan.
Hi, everybody. Thanks for coming today. If you haven't filled in your attendance, we will appreciate it if you could help fill in using the URL sent by Chun Seong. Other than that, thanks for coming. And now we'll be splitting into breakout rooms for playing games. So if you want to stay, feel free to stay and chat or play games. But if you have to go, feel free to leave as well. So yeah, thanks again for coming. clear skies.